Okay, so like I said, first slide. Today, where do we start? So today we need to start here. So when we're talking about plate tectonics, something that you kind of need to keep in mind is as these are moving around, they aren't all moving in the same direction. So some places you're going to have plates moving apart. Some places you're going to have plates coming together. And sometimes they move side or past one another. So all different types of movements and different types of plate boundaries that we'll talk about. But probably the most important one, or the most important type of boundary that drives the movement of the plates has to do with seafloor spreading. And it's just like what it says. It's where the seafloor is actually spreading apart. The plates are being pulled apart, and it's in the seafloor. So there was a guy, Harry Hess, back in World War II. He was working for the Navy, and he came up with this machine called the fathometer. It measures the depth of water by basically measuring how far from the surface to the bottom of whatever body of water you're in. If you are a Navy, if you have lots of large ships, if you have submarines, it's good to know how deep the water is. I mean, if you have any kind of boat, it's good to know how deep the water is, but especially if you have large ships with hundreds and hundreds of men on it, or a submarine that is completely underwater with no windows, it's good to know that. So it basically set out to map the ocean floor. Initially, scientists thought that the ocean floor was just smooth and just completely flat. And they've discovered that it was anything but flat. Basically, any type of geologic feature that we have on the surface, there's something similar on the ocean floors. So there are mountains, there are volcanoes, there are canyons, valleys, all of that. But it is definitely not just a smooth ocean floor. So one of the things that they had discovered while they were basically mapping the ocean floor were these things that they called spreading centers. And again, just like what the name says, it's a spreading center. It's where the ocean floor is being pulled apart. And when that happens, when those plates are pulled apart, then that's going to create an opening, and magma will flow into that, and then crystallize and solidify and become new rock. You can kind of think of it kind of like a cut. If you cut your hand, the skin's going to open up, bleed, it'll turn into a scab, and it'll be replaced with scar tissue. Kind of like that, similar, sort of, maybe not really, but sort of. But when this happens, when these plates are being pulled apart, something to keep in mind is, the rock that was at the very center is being pulled apart, and then new rock forms in the middle. And then that will be pulled apart and new rock will form. So, like this one, this yellow rock was in the middle. And now, since it's been pulled apart and then this blue rock is formed, now you have, that original yellow rock that's, gradually going to move further and further away from that spreading center. Something else that was discovered, not necessarily discovered, on the ocean floor first, was something called paleomagnetism. If you had a compass in your hand, today, the needle's going to point north. That's what we call normal polarity. The needle is responding to the Earth's magnetic field, is pointing to the North Pole. So like I said, that's normal polarity. But the polarity of the Earth hasn't always been that way. Every so often, that polarity flips. So if you were able to go back in time, 75,000 years or so, whatever, it's possible that if you had that same compass, you could step out of your time machine, look at your compass, and the needle would be pointing south because the polarity had flipped. So during those periods of time, when the polarity is flipped, we call that reverse polarity because it's the opposite of the normal polarity. Likewise, if you were to go into the future, if you timed it right, then, again, it could potentially, be reverse polarity. It could be normal polarity. So how that relates to seafloor spreading and all that, and how this has been kind of discovered or measured, the way that we know what the magnetic field was in the past, in areas where there has been volcanic activity. In the magma and the lava are tiny bits of iron, and iron reacts to magnets. In order for a magnet to be attracted to a metal, the metal has to have iron in it. That's why aluminum cans aren't attracted to magnets, because there's no iron in it. So when the magma and lava is still liquid, those little pieces of iron, little even microscopic pieces of iron, will align themselves just like a compass needle, and they'll either point to whatever the magnetic field tells it to. If it's normal polarity, it's pointing north. If it's reverse polarity, it's pointing south. And then that magma or lava will solidify and harden, crystallizes, and it locks those little bits of iron in place. So scientists take rock samples and make note of how that rock sample was oriented. They can determine if during the time period when that rock was formed, or when that rock solidified, if it was a normal polarity or reverse polarity. So relating to seafloor spreading and paleomagnetism, when they took samples on the ocean floor, they noticed a pattern. And as you moved from the spreading center outwards, in equal distance from each side, you had the same type of polarity. So this is, so if this was normal polarity now, and then it's reverse and normal reverse. And it's not always uniform the period of time, but it's usually fairly close. But this also tells us, that it is spreading apart, and that the ages of these bands of rock, so if we're talking about the age of the band of rock A, G would be the same age, because in the past A and G were in the very middle, and then they were pulled apart, just like B and F are the same age, C and E are the same age, and then D, which is right in the middle now, will be pulled apart, and then something else will form in the middle. So it's also, you can kind of think of it like a book, because it's a mirror image of it. So however far, if you go a mile this direction, a mile that direction, those rocks are the same age and were formed at the same time. So at these spreading centers, there are forces that are pulling these plates apart. These are obviously powerful forces. This is an example of probably the best known spreading center, the Mid-Atlantic Ridge. You can find the Mid-Atlantic Ridge in the middle of the Atlantic, just like the name says. Those plates are being pulled apart. Since those plates are being pulled apart, like I said, you have to have places where plates are coming together. So here you have, and we'll talk more about these, but you have what's called a subduction zone, where one plate is pushed underneath another one. So, you know, in those converging boundaries, you have subduction zones. Like I said, we'll talk more about those. But the forces that are actually pulling these plates apart, the biggest one, the most important one, is convection. And this is a concept, convection and convection currents. This is something I would I would highlight, you know, take a picture and make it your wallpaper on your phone or something, because this is something that we'll see, you know, see it now with convection currents in the Earth's mantle. You'll see it in liquids, in gases, so in the atmosphere. The convection currents form when something is heated up. It expands a little bit. It gets a little bit bigger. When that happens, that makes it less dense, so it rises. So that's why hot air rises, like a hot air balloon. You know, inside the balloon, if you heat up that air, it makes the air inside the balloon less dense, so it rises because it's essentially floating in the air that's around it, because the air that's around it is more dense. When things cool, they shrink and they contract a little bit, which makes them more dense, so then it sinks. So that's why if there's a house that has a basement in it or something, the basement's always cooler. Just like, you know, the top floor of a house is always warmer. Hot air rises, cool air sinks. Or if you have a lava lamp or have seen a lava lamp, there's a light bulb in the bottom that heats up wax inside. When the wax is really close to the light bulb, it gets warmer, so it expands and becomes less dense, so it starts to move up. And then it cools because it's further away from the heat source. It contracts, and then it starts to sink because it's more dense. It gets heated up again, becomes less dense, and goes up. So it's this convection current is just this up and down, you know, heating and then cooling and heating and cooling. So with the Earth and in the mantle, you have, you know, heating of material in the mantle that rises, and then it hits the crust of the Earth, and it can't keep going, so it spreads out. As it's spreading out, it cools, so it starts to sink back down towards the core, heat it up again, so then it starts to rise. So you end up, just like in this diagram, with these, you know, convection currents that, you know, kind of act like, you know, like a conveyor belt to pull these plates apart. It's not a fast process. I've heard it compared to the speed by which the plates are being pulled apart is about the same speed as your fingernails grow. So it's not a lot. I mean, it's not fast, but the Earth's really old. So if you start multiplying out, you know, that distance, say per year, you know, a couple of inches per year, maybe you start multiplying that out by, you know, hundreds of thousands, millions, then it can be a big change. But again, convection currents, this is going to be something we're going to see again and again. So I would kind of keep that, you know, in the back of your mind. Or if you have a quiz or a test or something and you have no clue, but convection or convection currents is an option, it would probably be a decent guess. I'm not saying that it's always going to be right. I mean, since it is something that comes up again and again and again, I mean, playing the numbers game, it might not be a bad choice. A couple of other forces that contribute to this, or to the spreading of the plates. Is the first one, or the second one, is ridge push. So as this material, actually I think I skipped one. This is just an artist's rendition of kind of what this process looks like. So you have this hot material, this mantle plume rising, you know, it's being heated by the core. It hits the crust, spreads out, and, you know, as it cools down, then it starts to sink, and then, you know, it's just creating those convection currents. So with ridge push, as that mantle plume rises and it hits the crust of the earth, it actually pushes it up a little bit. Well, anytime there's an angle, something wants to move down that angle. So since that mantle plume is pushing it up, now all of the plate wants to move down that angle. So there's some force from ridge push. And then the third one, slab pull. In a subduction zone, where one plate is being pushed under another, the part that's already being pushed down into the mantle, there's a lot of momentum with that. Not because it's moving super fast, but because it's huge. I mean, the mass that's involved in that portion of the plate is huge. So there's a lot of energy. There's also a lot of, it weighs a lot. So the weight and momentum of that portion that's already being pushed down into the mantle essentially pulls that plate down into the mantle, even further. One way to kind of think of it is if you have a piece of paper or a towel or a blanket or something on a table or a countertop, if you put the piece of paper over the edge of the counter, eventually the weight of whatever is hanging over the edge is going to pull it the rest of the way over. It's kind of like that, except it's just on a huge scale and it's, made of rock and all that. I think that's about it. Does anyone have any questions, or are there any slides I need to go back to? No? Okay. All right. Well, I'm going to